Welcome to another lecture on signals and systems. So in today's lecture, we'll be finding the impulse response of this feedback system. So this is a feedback system where y of t is delayed by t, then multiplied with a constant alpha, and then added with the input to give the output at the next instance of time. So let's write the equation governing this feedback system. So this is y of t. Here y of t is delayed by capital T. So the output here would be y of t minus t at this point. This is a delay operation which I covered in one of my previous lectures. You can click the link here and see how delay works. Then this is multiplied with alpha. So I get alpha times y of t minus t here, and then this is added with the input. So the total equation then becomes x of t plus alpha times y of t minus t is equal to y of t. Now in order to find the impulse response, we know that the input has to be a delta function, delta of t, and then the output of the LTI system when the input is a delta function is h of t, or the impulse response. So replacing x of t with delta t in this function, delta t plus alpha times h of t minus t is equal to h of t. And we are interested in finding h of t, which is the impulse response. So we are also given the condition that this system is causal, that is, it is non-anticipatory. And the requirement for an LTI system to be causal is that h of t has to be 0 for all t less than 0. So we can solve this equation recursively. So starting from t equal to 0, we know that delta t exists only at t equal to 0. So delta of 0 plus alpha times h 0 minus t is equal to h of 0. So putting t equal to 0, because we know the impulse response has to start at 0 because this is a causal system, and delta t only exists at 0. So we get from this equation 1 plus alpha times h of minus t would be 0 because impulse response has to be 0 for t less than 0. So alpha times 0 is equal to h of 0. And from here I get h of 0 equals to 1. Now I can put t is equal to capital T, which is the time delay. So if I add this into this equation, let's call this equation number 1, then we see that the equation becomes delta t plus alpha times h of t minus t, which would be 0, is equal to h of t. And delta t we know only exists at 0. It's an impulse at t equal to 0. So the impulse response at t is equal to alpha times h of 0. And what is h of 0? We found here that h of 0 is equal to 1. So I get h of t is equal to alpha. Similarly, I can find the impulse response at t equals to 2t. This would be from equation number 1, delta of 2t, which again I know goes to 0 because delta only exists at t equal to 0, plus alpha times h of t this time. Well, I would have 2t minus t here, and this would be equal to h of 2t. And what is h of t? H of t I know is equal to alpha, so my h of 2t is equal to alpha square times 1. So h of 2t becomes alpha square. So if I extend this to find the impulse response at n times t, then this would be equal to alpha to the power n. So depending on the multiple of the delay, alpha is raised to that power. So I can write my h of nt is equal to alpha times n. So this, if I want to write in the form of the total impulse response. So what we have found out is that h of 0 is equal to 1. So there has to be a delta function at t equal to 0. Then we have alpha times delta of t minus t, because this was equal to h of t. Then alpha square times delta of t minus 2t. So this is h of 2t. If I go on like this, I would have alpha to the n delta times t minus nt, which is the impulse response at the nth delay, h of nt. And therefore, this is the total impulse response of the system. So that's it for today's lecture. In the next lecture, we'll look at some other topic related to signals and systems.